Hello, and welcome to this video on molecular and empirical formulas. We will be focusing on understanding these fundamental chemical representations. Chemical formulas are symbolic representations of molecules. They are essential for understanding molecular structure and bonding, providing information on the types and number of atoms present. The molecular formula shows the exact number of atoms in a molecule. For example, the molecular formula for glucose is C6 hydrogen oxide. Subscripts indicate the number of atoms, following standard conventions like carbon, then hydrogen. The empirical formula is the simplest whole number ratio of atoms in a compound. It reduces the molecular formula to its lowest terms. For example, the empirical formula of glucose, hexacarbon dodecahydride O6, is CH2O. To determine the empirical formula, first convert mass percentages to grams, assuming a 100-gram sample. Then convert grams to moles and find the simplest whole number ratio to write the formula. Let's practice determining empirical formulas. The problem asks for the empirical formula of a compound with 15.8% carbon and 84.2% sulfur. Here is the calculation for the compound with carbon and sulfur. By assuming a 100-gram sample, converting to moles, and dividing by the smallest mole value, we find the empirical formula is CS2. This scene is intentionally left blank. You can convert between formulas using a whole number multiplier n. The molecular formula equals the empirical formula multiplied by n. For example, ethene, C2H4, and butene, C4H8, both reduce to the empirical formula CH2. There are different ways to represent molecules, including structural, condensed, and skeletal formulas. These representations provide varying levels of detail about the arrangement of atoms and bonds. Structural formulas introduce more detail than molecular formulas. They show the arrangement of atoms and indicate chemical bonds, which is essential for understanding molecular geometry. Bond-line structural formulas are common in organic chemistry. Carbon atoms are at vertices, hydrogen atoms are often omitted, and bonds are shown as lines. The importance of 3D structure cannot be overstated. Molecules exist in 3 dimensions, and different spatial arrangements affect properties. Wedge and dash notation is used to show this 3D structure. Common molecular examples include water, H2O, methane, CH4, and glucose, C6 hydrogen oxide. These examples help illustrate how molecular formulas represent compounds. Practice exercises involve converting molecular to empirical formulas, identifying possible molecular formulas from an empirical formula, and drawing structural formulas for simple molecules. To avoid common mistakes, remember to reduce to the lowest terms for empirical formulas. Also, ensure correct atom ordering and avoid missing bonds or incorrect valence electrons in structural formulas. These formula concepts have many applications in chemistry, including mass calculations, structural analysis, property prediction, chemical reactions, and synthesis planning. Strategies for assessment include exercises in converting between formula types, drawing structural formulas, identifying empirical formulas, and molecular visualization exercises. Advanced concepts involve resonance structures, isomers, and the study of complex organic molecules, coordination compounds, and polymers. In summary, molecular formulas show exact composition, empirical formulas show the simplest ratio, and structural formulas show atom arrangement. These multiple representation methods are essential for understanding chemistry.